Head sampling discards traces before failures appear. OpenTelemetry cannot recover a slow request it never kept. You'll configure OpenTelemetry tail sampling to retain error and slow LLM traces while keeping a 5% routine baseline. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. LLM requests can look healthy at the start, then fail after a model timeout, or become slow during generation. If your application samples too early, the traces you need most may already be gone. Tail sampling changes that decision. The collector waits until a trace finishes, then keeps it because of what actually happened. We will send complete LLM traces to a local collector and let it retain the important ones. That gives you useful debugging data without paying to store every normal request. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, the application must export every trace so the collector can make an informed decision. This snippet configures OpenTelemetry to export every Python trace to a local collector over OTLP. The key choice is always on in tracer provider, which means the Python service does not discard traces at the start. Head sampling cannot recover a trace rejected before an LLM error or final latency is known. Batch span processor gathers completed spans efficiently. Then OTLP span exporter sends them to the collector. Resource labels the source service as LLM API, so retained traces can be identified later. The printed result confirms that AlwaysOn sampler is active, leaving the final keep or drop decision to the collector. Now that every completed request reaches the collector, we need routine traces with useful but safe measurements. This example emits a successful LLM request span through the configured OpenTelemetry tracer. Routine requests create most of the trace volume, yet sampled examples still need enough context to explain model usage and payload size. Tracer.startAsCurrentSpan creates the LLM.requestSpan around the request work. Span.setAttribute records the model name, prompt length, and response length without attaching the full prompt or model answer. That keeps the trace useful while reducing exposure to sensitive text. The printed response size confirms that the exported span carries a concrete request measurement the collector can preserve when this routine trace is selected. Successful requests are useful for a baseline, but failures need an unmistakable signal before the trace closes. This code marks a model timeout as an OpenTelemetry error before the span finishes. A collector's status code policy makes decisions from the completed span status, so recording an exception event alone may not communicate the intended sampling signal clearly enough. Span.recordException keeps debugging detail about the timeout. Span.setStatus then assigns status code.error, which labels the finished trace as failed for the collector. This separation matters because one action captures evidence, while the other sets the trace outcome used by the sampling rule. The output confirms the error status that tail sampling can use to retain this failed LLM request. For more practical lessons on AI engineering and observability, please subscribe. Errors are clear, but a request can be successful and still be too slow for users, so the collector needs rules for both cases. This snippet defines 3 OpenTelemetry Collector tail sampling policies for high-value LLM traces. The status code policy retains traces marked error, so model failures do not disappear into a random sample. The latency policy retains a request when its complete trace lasts at least 2 seconds. That catches slow generations, retries, or tool calls even when they eventually succeed. The probabilistic policy keeps 5% of routine traffic, giving you a small baseline for normal behavior. Raising sampling percentage improves routine coverage, but it also raises ingestion and storage cost. The output confirms that 3 complementary policies participate in each completed trace decision. The policies are ready, and the last step is wiring them into a collector pipeline that can be checked before it runs. This example assembles and validates a complete OpenTelemetry Collector traces pipeline. The OTLP receiver accepts spans exported by the Python application. Tail sampling waits until traces are complete, then applies the error, slow request, and routine fallback decisions. The debug exporter exposes retained traces locally, which makes it easier to verify behavior before sending data to an observability backend. Subprocess.run invokes otelcol-contrib validate through the documented env configuration provider. That catches malformed component names or broken policy structure before deployment. The output shows a 0 validation exit code, confirming that the collector can load the error, slow trace, and fallback sampling pipeline. When traffic grows, watch how long the collector must hold traces before deciding. Tail sampling needs memory for in-progress traces, so very high request volume, long generations, and traces that never finish all deserve limits and monitoring. Head sampling still fits low-cost metric-style visibility, but tail sampling is the better choice when the final outcome determines whether a trace matters. This example keeps errors, captures requests that take at least 2 seconds, and preserves a 5% picture of normal LLM traffic. The important shift is simple. Let the request finish before deciding whether its trace is worth keeping. Try changing the routine sampling percentage and compare the extra coverage against the storage cost. You can also lower the latency threshold if users expect faster responses and slow requests need earlier attention. Tell me what practical observability topic you would like covered next, such as trace attributes, prompt privacy, or debugging tool calls. Subscribe if you want more clear Python lessons for building reliable LLM systems.